Welcome back to the Deep Dive. Today we've got the blueprints for, well, the future of AI infrastructure. And our mission is a big one, mapping the optical revolution.
It's a critical deep dive. I mean, the entire world of AI, and we're talking about the massive demand for data movement, trillions of parameters.
Right.
It's fundamentally breaking the physical limits of electronics. The era of copper wiring is, well, it's hitting its endgame.
That's the core challenge right there. We're tracking how light is replacing electrical current as the transport medium in the data center. We're going to explore the radical science, the architecture, and the industry titans really powering this shift.
And the urgency is impossible to ignore. It truly is.
I mean, the numbers are just staggering.
They are. If you look at the raw projections, the crisis is immediate. Global data center power consumption, it's projected to surge by what, 165% by 2030?
Potentially hitting 219 gigawatts. It's an insane number.
But that huge number doesn't even convey the real problem, which is the inefficiency.
Tell us about the waste. This is the statistic you pulled that it floored me.
In 2024, nearly 30% of an AI cluster's total energy was squandered. Literally wasted.
Not computing?
No, not computing, just moving data between the chips. Imagine putting gasoline in your car, and I don't know, a third of it is just consumed by heat generated in the fuel lines before it even gets to the engine.
30%. That means scaling AI is no longer just a matter of speed. It's now a matter of efficiency.
Exactly.
The energy per bit is the absolute critical metric. It defines whether these trillion-parameter models are even economically feasible or if they're just a massive power sink.
It is, and that puts the spotlight squarely on copper's limitations. I mean, electrical signals degrade so rapidly. Copper is limited to, around 100 meters for high-speed transmission?
And it's bulky, it's susceptible to electromagnetic interference.
Which is terrible, and dense, noisy racks, and the power consumption is immense.
We're talking 5 to 8, maybe more watts.
And more, yeah. Just to run a single high-speed 10G copper port.
Whereas
a fiber optic link can do the same thing for less than 1 watt. Plus, light is immune to EMI. Look, copper worked for decades, but for AI scaling, it's just this inefficient, power-hungry bottleneck.
Yep.
The electrical age of the interconnect is over.
Okay, let's look at the immediate solution, which is architectural. It's not just swapping a cable. It's co-packaged optics, or CPO.
Right.
The sources often refer to this copper bottleneck as the shoreline limitation. I love that description. For you listening, what does that actually mean?
It's a great visual, isn't it?
Yeah.
Imagine the perimeter of your GPU or your ASIC chip is a shoreline.
Okay.
As that chip gets exponentially faster, the total bandwidth going in and out just explodes. You need more and more physical input-output pins, more I/Os on that chip perimeter to handle all the electrical signals.
But the physical perimeter of that shoreline, it's fixed. It doesn't get any bigger.
Precisely. You literally run out of beach. You run out of room for electrical pins long before you run out of processing power. It's a geometry problem.
A physical
wall. And CPO solves this by completely re-architecting the system. It moves the interface from that noisy, crowded electrical realm to the efficient optical realm, as close to the chip as physically possible.
So how close are we talking? What does the co-packaged part really involve?
It means we move the critical component, the converter that takes the electrical signal and turns it into light.
The optical engine?
Yeah, the optical engine, or the photonic integrated circuit, the PIC. We move it directly next to the compute chip, like the ASIC or GPU, on a shared substrate. They're basically neighbors in the same tiny package.
I see. So that's a radical physical shrinkage. Instead of having these long electrical traces snaking across a whole circuit board to some separate transceiver module.
You bypass all of that. We shrink that critical path from, potentially several lossy centimeters down to just millimeters inside the chip package.
And that shortness.
Yeah.
That's the key to the massive power savings.
It is. Because it eliminates the need for something called digital signal processors, or DSPs.
Okay, we hear DSP mentioned all the time. For those of us who aren't electrical engineers, why were those needed in the old system, and why are they so power hungry?
Think of the DSP as like a cleanup crew for a noisy signal.
Okay.
When an electrical signal travels across a long PCB trace, it gets distorted. It degrades from interference, attenuation, it gets messy. The DSP's job is to run these complex, very power-intensive algorithms to essentially reconstruct that corrupted signal so the receiving chip can understand it.
So if CPO shrinks the electrical path down to just millimeters, the signal stays clean.
The signal stays clean.
And you don't need the cleanup crew anymore.
Exactly. You just fire the DSP. And that's where the power efficiency really, really kicks in. We talk about this in terms of picojoules per bit or PJ bit.
These are like fuel economy for data.
Perfect analogy. Older pluggable modules were running at maybe 15 to 20 PJ bit. A CPO system can cut that by 30 to 50%. It can achieve efficiencies around 5 PJ bit.
That's not just an improvement. That's the required leap to make these multi-rack AI systems viable at all.
It is, and it's an evolution. We're seeing it move through stages, right? It started with near-package optics, NPO, using 2.5D packaging. But the ultimate goal, the holy grail, is full 3D vertical stacking.
Where the optics are stacked right on top of the compute chip.
Yeah.
The tightest possible integration.
That's where the heat management gets truly, truly challenging. But the efficiency gains, they're just irresistible.
Okay, so this is where it gets really essential to look at the players. The industry titans are in a full-on arms race to deploy this. From a manufacturing perspective, who's making the first big moves?
You have to start with TSMC, the foundry powerhouse.
Of course.
Their whole CPO strategy is built on this platform called ECUEE, the Compact Universal Photonic Engine. They're leveraging their most advanced 3D stacking, the SOIC-X, which uses something incredibly complex called bumpless hybrid bonding.
Bumpless hybrid bonding. That sounds like the manufacturing equivalent of building a watch at the micro level. What does that mean for the end product?
It means they can fuse the electronic chip and the photonic circuit together at a nearly atomic level, which minimizes resistance and maximizes the thermal and electrical connection. And crucially, they've qualified the key optical component, the mechanism that actually switches the light, the micro-ring modulator, or MRM.
Okay, give us the simple version of an MRM. What is it?
Think of it as a microscopic, ultra-high-speed shutter for light. It's a tiny circular waveguide that uses electricity to modulate the light passing through it. It's what lets you encode data onto the photon beam at insane speeds.
And TSMC has qualified this.
On their cutting-edge 3-nanometer process node, they are targeting 1.6 terabit samples next year, 2025, and then volume production in 2026. This is the foundational piece. This manufacturing feat is what makes everything else possible.
So then you've got a giant like Intel leveraging decades of expertise in silicon photonics.
Right. Intel demonstrated its own optical compute interconnect, the OCI chiplet. They ran live data, co-packaged with a CPU, and showcased a staggering 4 terabits per second of bidirectional transfer.
And they hit that magic number.
They hit that magic 5 PJ bit efficiency, even in the prototype. So Intel is taking that chiplet approach, making optics modular.
NVIDIA, of course, isn't just watching from the sidelines. Their strategy is more about integrating optics deep into their networking fabric, isn't it?
That's the key for them. NVIDIA is deploying CPO with its Quantum-X Photonics InfiniBand switches. For NVIDIA, it's not just about power, it's about system reliability.
Right, because traditional pluggable transceivers were a notorious point of failure in these massive AI clusters.
A huge point of failure. By integrating the optics directly with CPO, they're claiming a 10 times higher system resiliency.
That's an enormous operational benefit. I mean, reliability translates directly into dollars when you're running billion-dollar training jobs.
Absolutely. It means you can run those massive AI workloads 5 times longer without an interruption. They're also building in things like in-network aggregation to accelerate the training. It's a holistic strategy where the interconnect is now really part of the compute fabric itself.
Okay, finally, let's talk about the huge strategic move by Marvell to conquer that fabric layer. This really speaks to the so what of this whole optical shift.
The $3.25 billion acquisition of Celestial AI late last year, that was monumental.
A huge deal.
Marvell is focused on leveraging Celestial's Orion photonic fabric to create what they're calling a memory-first architecture. It's designed to allow hundreds of XPUs, your GPUs, your accelerators, a multi-rack setup to operate with full memory coherence.
And that concept, memory coherence, is so critical for anyone trying to scale large models. Explain the fundamental problem they're solving there.
They are solving the stranded memory problem. It's a critical bottleneck. When you have an AI model spread across multiple racks, the expensive, super-fast memory attached to GPU-A might just be sitting there, idle.
Doing nothing
For milliseconds, which is an eternity. Why? Because the data it needs is on GPU-B's memory and then next rack over, and the electrical interconnect is just too slow to fetch it in time.
So the GPU, the most expensive and powerful piece of hardware in the whole system, is just sitting there, waiting for data.
Precisely. It's stranded. By using the Orion photonic fabric, Marvell's goal is to make all memory across the entire cluster appear local and instantly accessible. Light fixes that data access delay. It ensures those GPU compute cycles are never, ever wasted.
That is how you truly scale generative AI.
A powerful transition.
Okay, let's move from the architecture CPO to the medium itself, what the light is actually traveling through. Let's talk about hollow core fiber, or HCF.
HCF is the materials science breakthrough that really completes the picture. We've optimized how we launch the light with CPO.
Right.
Now we optimize how fast it travels. Traditional fiber guides light through a solid core of silica glass. HCF replaces that dense glass with basically an air-filled channel,
So it's guiding the light through air.
guiding it through air using this specialized microstructured cladding.
Why does replacing glass with air give you such a dramatic performance boost?
It's just physics. Light travels nearly 50% faster in air than it does in solid glass.
50%.
The result is a dramatic reduction in latency. We're seeing a 30 to 47% lower latency compared to standard fiber.
Now, we're talking about tiny measurements here, right?
Yeah.
Microseconds per kilometer. But in an enormous synchronized AI cluster, those microseconds have to stack up incredibly fast.
They absolutely do. The sources cite a difference between, say, 4.9 microseconds per kilometer in standard fiber versus 3.3 in HCF. That difference is critical when you have tens of thousands of GPUs all needing to synchronize their data updates for a massive training run.
It shortens the training time.
It cuts weeks off a training schedule. This speed is literally the difference between an AI product launch succeeding or failing against a deadline.
And beyond the performance inside the data center, the application for real estate is fascinating.
It completely changes the economics of where you can build a data center. HDF extends the effective latency threshold for these high-speed connections from around 60 kilometers to 90 kilometers.
So suddenly operators have.
2.25 times more buildable space to choose from around major peering points.
That's massive. It means you can move outside of these expensive, dense urban areas. You can pick locations based on cheaper power or, more critically, better access to renewable energy.
Without sacrificing network speed. Exactly. And this isn't some theory. Microsoft Azure is a key adopter. They are already expanding HCF deployment across their global network. It's production ready. It's a game changer for sustainability planning.
So if we zoom out, what does this all mean? How are optics shaping the entire data center ecosystem way beyond just the GPU interconnects?
Well, it all comes back to thermal management, to heat. The incredible density of CPO and the sheer power of AI racks. We're talking 50, even 100 kilowatts per rack.
Air cooling just can't keep up.
It's obsolete. Fiber's lower power consumption helps a little, but liquid cooling is now an absolute necessity.
And companies are actually integrating fiber directly into those cooling systems.
They are. You look at a company like Micros Technologies. Their micromatrix cold plate uses this array of microchannels for superior heat transfer. This high-density design lets you pack an unbelievable amount of fiber into a tiny space.
Like what?
For example, a single 1U compute tray that's the size of a pizza box can hold over 11,152 optical fibers. That density is it's unachievable with the bulk and heat of electrical connections.
And it seems like fiber optics are also starting to bridge that gap between classical accelerated computing and the nascent field of quantum computing.
That's where something called NVQ-Link comes in. It's designed as this universal interconnect. It links the workhorse's NVIDIA GPUs directly to specialized quantum processors.
To enable these large-scale hybrid workflows.
Right. You use the classical computer to manage and control the quantum system, and that requires extremely low latencies.
And the sources show that latency is the difference between a functional quantum computer and one that just generates errors.
It is. The low microsecond latency of NVQ-Link is essential for real-time error correction. In a test with a Continuum QPU, the system maintained 99% fidelity with the correction applied.
And without it.
Only 95% fidelity without it. The speed of light is directly enabling usable quantum computation.
And finally, let's talk about the manufacturing process itself. Optics aren't just transporting data anymore. They're ensuring the chips are built correctly in the first place.
Yeah, fiber optic sensing, or OFS, is now a critical tool in making semiconductors. Specifically, fiber Bragg grading sensors and distributed fiber optic sensing.
DFOS.
DFOS, yeah. They're used for incredibly high-precision metrology in EUV lithography and in clean rooms.
So the fiber itself is the sensor, constantly monitoring the environment.
Precisely. These DFOS systems, they use the properties of light scattering inside the fiber to continuously monitor temperature with remarkable accuracy. Down to zero point 0.1 degrees Celsius across the entire fabrication environment, they monitor structural integrity, thermal profiles.
And why is that level of precision so necessary?
When you are operating a multi-billion-dollar EUV lithography machine, the absolute slightest thermal drift can ruin an entire wafer of chips. This predictive, high-accuracy monitoring is essential for maintaining that perfect environment you need to build chips at the 3-nanometer scale and beyond. Light is now overseeing its own manufacturing.
We've covered a massive transformation today, and it's all driven by the simple failure of the electrical interconnect. So, to synthesize the three core changes that you, our listener, really need to carry forward. First, that fundamental shift from copper to fiber. It solves the problem of bandwidth and distance.
Second, the architectural change to co-packaged optics, CPO. That solves the crippling issues of power consumption and density right at the chip level, which is what enables multi-rack AI.
And third, the material science shift to hollow core fiber, or HCF. That solves the final frontier of latency, which is essential for training synchronization and for optimizing where you can even build a data center. This confluence, it's dismantling the physical limits that really threaten to derail AI scaling entirely.
The interconnect bottleneck, for this generation at least, has been shattered.
We've seen light replace electrical signals for communication, and the industry is already looking to what's next. So if silicon photonics has solved the bottleneck for data movement, the ultimate question is, what happens when companies successfully move beyond communication and start solving computation using light itself, the realm of all optical computing?
That is the next paradigm shift, solving problems literally at the speed of light.
Absolutely. The cutting-edge research is focusing on things like optical matrix vector multipliers, where neural network calculations are performed with photons instead of electrons. So what new problems will we face when the chips literally run on light, potentially generating almost zero heat? We encourage you to explore that idea, that zero heat future, and the profound implications it holds for the entire global energy footprint.